Welcome back from the break. I hope you all enjoyed the cinnamon buns. We're now going to talk about parallel streams, I think. And we welcome Mr. Brian Goetz. He's a Java architect, language architect from Oracle. So take it away.
Thank you. Hello. So how many people here have tried out Java 8 and the streams library? How many people like it? All right, good. So as most of you know, the streams libraries allow you to specify a computation and separately from how it's going to be executed. You can say, here's the computation I want to do, and then separately you can say, do it sequentially or do it in parallel. So what this talk is mostly about is how to judiciously use that capability of deciding whether a computation should be sequential or parallel. So obligatory Oracle slide. This is how you know I'm not an imposter. OK, so to talk about parallelism, let's take a look for a minute about the hardware context in which our programs run. So this is a graph some of you have probably seen before. Each of the dots in this graph represents an Intel CPU release. And the green curve represents the number of transistors in that CPU. The y-axis is a log scale. So we see an exponential increase in transistors per chip over time, which confirms what Moore's law tells us, which is that the number of transistors that you can cram on a chip doubles approximately every 18 months. The blue line tells a somewhat more unfortunate story. The blue line, the dark blue line, is the clock rate of those chips. So for a good 20, 25 years, we got a nice exponential increase in clock rate, which meant that if you had a hard problem to solve, all you had to do was wait a year or so for the new chips to come out, and your problem would get easier. And that game was great. It worked well for 25, 30 years. And then around 2003, that game completely ran out of gas. And what you see is that clock rates maxed out somewhere around 2003. The two other curves sort of tell a story about why. The light blue curve is the power that chips take. We basically hit the wall of how much heat we're willing to let our chips generate. And the purple line is a measure of what we call instruction-level parallelism. That's basically the amount of parallelism within the chip that we get from tricks like pipelining and superscalar execution and out-of-order execution and speculative execution and all those amazing wacky tricks that hardware designers do. But what we see is that all of these things essentially ran out of gas at the same time. So Moore's law hasn't been repealed. We're still getting more transistors every year, but we're not getting faster cores. The best that Moore's law could do for us is give us more cores. And so you would think that if we took the Moore's law dividend and plowed it entirely into just giving us more and more cores, we would see an exponential increase in the number of cores on a chip. And that's certainly what was predicted about 5 to 10 years ago. Now, what actually happened is something slightly less than that. So the red line shows what an exponential increase in core count would have predicted based on where we were in 2005 or so. And the blue dots represent actual Intel Enterprise EX processor releases and their core counts. And we do see that they're increasing, but they're not increasing nearly as fast as they could be if we plowed the entire Moore's law dividend into more cores. So why? Why are the chip makers not delivering all the cores they can? Is it because they're lazy? No. It's because we're incompetent, right? We as software developers can't use all those cores. The software we write is not able to keep those cores busy. So if they, if they were able to deliver a 1,000-core chip, for a rack mount server, we wouldn't know what to do with it. We wouldn't be able to keep those cores busy. We wouldn't be able to use all the cycles that we're paying for. Now, there are a couple of bright spots in this story. There are a couple of areas where we are able to exploit the kind of parallelism that the hardware could give us. GPUs is the best example. GPUs are massively parallel, and we use them for really important tasks like playing video games. But in the realm of things that we might do commercially, data parallel analytics is kind of the best option that we have, the best opportunity we have for using all the cores that the chip makers can give us. So concurrency has, for the most part, always been a tool for performance. You have this relatively expensive machine. You want to get all the cycles you paid for. Sometimes we use concurrency for structuring our programs, in models like CSP or actors. But for the most part, we use concurrency to maximize the amount of performance we can get out of a chip. Now, over time, the technique that we use for doing that has changed. So back in the old days, when we only had one core, we use concurrency mostly to get blocking operations off the CPU and into the background. So if you were doing a blocking I/O, you would run it in another thread so that something else could use the CPU. Or if you were doing a background task, you would run it in another thread so that something else could use the CPU. But that was mostly about asynchrony and non-blocking. As the number of core counts started to pick up, and when you started to see machines with 2, 4, 8 cores, we started to use concurrency more for task-based concurrency. You've got a server application, it's taking a bunch of requests, and if you have multiple cores, you can service multiple requests at the same time and get more throughput through the machine. And so, this model of sort of coarse-grained task-based concurrency was pretty successful about, in the time frame of maybe like 10 years ago to now. And this is, like I said, largely aimed at improving our throughput. As we start to have more cores, we may find we have more cores than we have tasks to execute, and we have to dig deeper to find ways to exploit those cores. And we start to shift from our focus from throughput to latency. If I have more cores available, can I use them to solve a problem faster and get the answer faster? Because if I can get the answer faster, maybe I can use it to make a decision more quickly. So the tools that we have for concurrency haven't changed that much, but the goals that we have for using concurrency have changed over time as the hardware has changed. And this sort of reflects a bigger picture. The way we write software is a reflection of what our hardware looks like. So we're all kind of a little bit lazy. We all follow the path of least resistance. So the programs that we write are the ones that are most natural to express in whatever language or frameworks we're using. And the same thing is true one level down. The people writing frameworks and languages do things in a way that's natural to express on the hardware you're running on. So if you look at, for example, the support for concurrency in the Java libraries, it kind of follows the trend of the hardware. In the Java 1.0 days, we supported concurrency in the language. We had built-in primitives for threads and locks and condition queues. But this was largely aimed, at asynchrony, background tasks, asynchronous I/O, etc. As we entered the multi-core era, Java acquired the Java Util Concurrent library in Java 5, which gave us tools like concurrent data structures and thread pools and blocking queues and semaphores, which were well suited to the sort of task-based parallelism that made sense for that kind of hardware. As data parallelism started to become more popular, we added the ForkJoin library in Java 7, which made it possible, although not easy, to take a computational problem and decompose it so that it could run well on multiple cores. And in Java 8, when we added the streams library, we added the ability to say, take this calculation and make it parallel. And that uses ForkJoin under the hood, but it is a much more pleasant way to use ForkJoin than using it directly. So as the hardware changes, that changes the kind of problems that we think are solvable on the hardware, which drives trends for language design, framework design, library design. OK, let me do some quick terminology. The terms concurrency and parallelism are, unfortunately, they don't have standard definitions. Almost nothing in computer science has standard definitions. But we often make the mistake of using them interchangeably. We often use either concurrent or parallel to describe two things basically happening at the same time. Now, there's a historical definition of concurrent versus parallel, which I'll give you, but I don't actually find particularly useful anymore. But I'll give it to you so that you can see the contrast from the newer definition. Historically, concurrency was a property of a program. It had to do with the structure of your program. Was your program structured as a monolithic sequential path of execution, or is it structured as multiple cooperating entities passing messages to each other, waiting for each other, etc. And historically, parallelism was a measure of the program's execution. Were things actually executing at the same time, or did it just look that way through tricks of scheduling? So in this model, concurrency is the potential for parallelism, but not a guarantee of it. And this was a really useful distinction in 1970 when true concurrent execution was really mostly a theoretical concern. It's a less useful distinction today. So the distinction that I think is more useful today, and this is what a lot of educators are using for these terms, is to say concurrency is about correctly and efficiently controlling access to resources, to data, to I/O channels, whatever. So a good example is you've written a data structure, you've got a bunch of threads, putting elements in the data structure, taking elements out of the data structure, and you want it to continue to work. You want the elements that come out to be the elements that went in. And ideally, you'd like it to work efficiently, so that multiple consumers can use the data structure at the same time without necessarily always waiting for each other. So the primitives that we use in concurrency are things like locks and events and semaphores and such. Now I'll contrast this with parallelism, which is about using more resources to get the answer faster. I've got a big data set, I'm searching for the needle in the haystack. If I divide it into two smaller haystacks and I'm able to search those haystacks in parallel, I might find the needle faster. So, okay, why should we care about this distinction? Why should we change the definitions that have been used, successfully for many years? Well, the real reason is parallelism is so much easier than concurrency. Concurrency is hard. I know a little bit about this. Reasoning about shared state and locks is really hard. It requires wizardry. And even if you have access to the secret wizard spellbook, it's still hard. On the other hand, parallelism is really easy. You clean that room, I'll clean this room. You grade those papers, I'll grade these papers. All you do is partition the task. One worker works on one part, another worker works on another part. In the end, maybe you meet up, to combine your results. That's a lot easier than reasoning about shared states and locks. All it requires is a sensible way of partitioning and a little bit of discipline so you don't step on each other's feet. So if you want to use parallelism effectively, we have to realize that if it's just about getting to the answer faster, then it's strictly an optimization. It's not intrinsic to your algorithm. And if additional resources aren't available, you can still get the answer doing it sequentially, just potentially slower. So if that's the case, we can flip this around and say parallelism is only useful if it actually does get you the answer faster. And just because we're using more resources doesn't mean we're going to get to the answer faster. We might get there in exactly the same amount of time. We might even get there slower, because sometimes it's more work for multiple workers to coordinate than for one to just do the whole job by themselves. So if you're going to use parallelism, you're signing yourself up for a certain amount of measurement and a certain amount of analysis. So first of all, you have to ask yourself, do I need the benefit parallelism offers me? If you don't bother. If you think you do, look at your problem. Analyze whether it's amenable to parallelism. If you use parallelism, then you have to measure to see, is it any faster? And this may involve a certain amount of iterating because maybe your first attempt wasn't as good as you'd hoped. But in general, we should prefer a sequential implementation unless we have evidence that a parallel implementation is both needed and effective. So how do we measure the effectiveness of a parallel implementation? We do so by speed up. We compute the ratio of the runtime in parallel to the sequential runtime. We say how much faster is it or how much slower is it. So it stands to reason that a parallel computation is always going to be more work than the best possible sequential implementation for the problem you're solving, right? How could it be otherwise? You still have to solve the problem, and you have to do extra stuff. You have to divide the problem. You have to manage the tasks. Maybe you have to fork tasks off. Maybe you have to wait for the completion of tasks. Maybe you have to coordinate between them. Maybe you have to combine the results. So you're doing all the work to solve the problem, plus you're doing all of this mechanical work to manage the parallel execution. So a good way to think about it is when you solve a problem in parallel, you're always kind of starting out behind the sequential solution, and you're hoping to catch up through the efficiency of having more workers working on the problem at once. So in order for that to actually work out, we need a bunch of things to happen. We need to have a problem that's parallelizable in the first place. Not all problems are parallelizable. We need to have an implementation of the solution that's actually amenable to parallelization. That's not the same thing as the first thing, right? You can have a parallelizable problem and have a completely non-parallelizable implementation. You also need good runtime support for things like task management, because otherwise you're going to get eaten by coordination costs. And most importantly, you need to have enough data in order for the benefit of parallelism to work out. And a reasonable way to think about this is, if you're like clearing the dishes from the dinner table, you don't need to have a strategy for how multiple people are going to work together. You don't need to say, I'll get the plates, you get the spoons. That's more work than just doing it yourself. But if you have a banquet hall where 500 people have just finished dinner and you want to clear the plates, you're going to benefit dramatically from parallelism. It's going to take you a long time for one person to clear all those plates. So you need to have enough data that the benefits of having multiple workers is going to kick in. So let's take a look at some problems. I've got two problems here. They're both defined as recursive problems. And the question is, do they parallelize equally well? All right, so I start out with some function f. Don't know what f is, but let's assume there's no inherent parallelism in computing f. And the function g is start with f of 0, and then feed it to itself. So f of 0, f of f of 0, f of f of f of 0, et cetera. That's what g is. The function h here is a little bit different. I'm saying start with f of 0, and then to get the next element in my sequence, add f of 1, add f of 2, add f of 3. And the question is, can I parallelize either of these computations? Can I parallelize both of these computations? And at first look, you would think that they would be equally parallelizable because they're both defined by recursion. But that turns out to be not true. So let's break them down. So in the first one, where I'm computing the sequence f of 0, f of f of 0, f of f of f of 0, et cetera, parallelism is a lost cause. No matter how many threads I have available to work on this problem, I have a data flow dependency where none of them can actually make any progress until the previous one finishes. So this is a problem that is fundamentally sequential. There's, unless I can exploit some parallelism computing f, I'm not going to get any benefit no matter how many resources I throw at this problem, because the data flow graph is essentially linear. I can't compute the next element until I've completely finished computing the previous element. On the other hand, the function h, which looks a little bit similar, is actually quite parallelizable. But if I took a naive implementation and implemented it straight off of the definition, I would get a data flow graph that looks like this, which still has me sequentially computing f of 0, f of 1, f of 2, f of 3, et cetera. But this is not the only way to compute this. I can rewrite this function. And the way I can rewrite it is saying h of n is really f of 1 plus f of 2 plus f of 3 plus f of 4, et cetera. And I can compute f of 1 and f of 2 and f of 3 independently. Those are, completely parallelizable. In fact, we call this embarrassingly parallel. That's when a problem is so amenable to parallelization that there's almost no coordination overhead. We call it embarrassingly parallel. So this is an example where we have an accidental data flow dependence, just because of how the program is written down. But if we rewrite it a little bit, we can get a data flow graph that looks like this and extract a lot of parallelism from this problem. So the point of this little example is some problems are parallelizable, some are not. But even if you have a parallelizable problem, you can easily implement it in such a way that your implementation will not be able to extract any parallelism. So you have to have exploitable parallelism. You have to actually exploit the parallelism. And those are two separate things. It turns out, unfortunately, that a lot of the techniques we're used to using from sequential algorithms get in the way of going parallel. And so we need to unlearn some bad habits. So let's take a look at a bad habit that we need to unlearn. So let's take our embarrassingly parallel problem, adding up the numbers from 1 to n, and think and look at the data flow graph we get from it. Now, if we write it in sort of the obvious way that we've been writing this kind of thing for years and years, we've introduced this data flow dependency. We get a computation tree that looks like this. First, add 0 and 1. Then take the result and add 2, then take the result and add 3, right? So this is another one of those accidental data flow dependencies. And where that comes from is the use of this accumulator pattern, right? So the computation tree that we really want to get looks more like this. So we need to write code that's amenable to this, and starting our program with int sum equals 0 is a surefire way to not get the computation tree you want. You're basically saying, you're introducing the sequencing into your computation, which is, say, start with the first element, then fold in the second element, then fold in the third element. That's a fundamentally sequential way to think. So how would we solve this problem in a more parallel way? Well, let's try a couple things. We could try to solve this using concurrency, right? So how might we do that? We might say, all right, imagine we have some magic primitive called concurrent that does 2 things at once. Okay, doesn't matter what the details are, just imagine we have this primitive. And let's divide our array in half, and we'll compute the sum of the first half, and we'll compute the sum of the second half, and then we'll add the results together, right? That seems reasonable. But this program is broken, right? This program is going to give you the wrong answer. It doesn't matter how fast it is, because it's going to give you the wrong answer. And the reason is we have a shared variable here, and we have 2 concurrent tasks banging on that shared variable. There's a data race on every access to the sum variable here. So we're going to get the wrong answer. Okay? Now, we can fix this, right? That's not so hard. One way we could fix it is by coordinating access to that shared variable. So imagine, in addition to our concurrent primitive, we have an atomic primitive. Takes a lock, uses STM, doesn't really matter how it's implemented. Now our program is correct. We're going to get the right answer. This is going to be even slower than the sequential version. And the reason for that is the threads are going to spend all their time sitting and waiting for the lock. And they're not going to be, you're not going to be using your cores to actually add numbers up, right? The whole point of using concurrency is to get all the cycles you paid for, right? You've got a computationally intensive problem, and you want to keep the cores computing. But when they're waiting for locks, they're not computing. So here's another example where we had a problem that had a lot of exploitable parallelism, but we failed to exploit it. Okay, so this goes back to a basic lesson about shared state. There's 3 ways to manage state. Don't share it, don't mutate it, or if you insist on sharing it and mutating it, coordinate access to it using locks. Now, it's a lot easier to get one of the first 2 right than to get the third right. Right? And when I said parallelism is easier than concurrency, it's because we're not sharing. I'm going to grade this stack of papers, you grade that stack of papers. There's no contention for access to papers. We're not coordinating at the word level or the sentence level. I've got my stack of papers, you've got your stack of papers. So let's try this approach and apply it to our problem. Let's try the don't share approach. So in this approach, we say partition the array into 2 chunks and operate on them independently. And the code for that is, pretty obvious, and it actually works. We have 2 accumulator variables. We have left sum and right sum. One task is adding up the left sum, one task is accumulating the right sum, and then at the very end, we merge the sums, and we get the answer. So now we're going to get the right answer, and we're probably going to get reasonable throughput and reasonable speed up if we have more than one core. So the basic theme here, and this is the theme throughout all parallel problems, is decompose the problem into subproblems, solve the subproblems independently, combine the results. Now, how's this going to perform? Well, if I have one core, it's going to perform about as well as the sequential version. It's going to perform a little bit worse because I'm going to do a little bit of work to fork off two tasks and wait for them to finish. But it's going to be on the on the order of as fast. If I have 2 cores, it should be on the order of twice as fast. Still have some overhead, which is a fixed overhead of forking off those two tasks, but if I have enough data, I will gain enough efficiency because those two cores were kept busy. Of course, if I have more than two cores, I'm not doing anything about it. I've only divided the problem into two, and it doesn't matter how many workers I have to solve the problem if I only have work for two workers to do. But this gives us a hint about where to go. Right? We can divide the problem more finely so that the number of buckets of work and the number of workers are more closely matched. But notice, we don't have any shared access to mutable state, and we don't have any locking, right? And locking is a big thing that slows you down because, while you're in the middle of doing something that should be computationally intensive, you have to stop and wait for a lock, right? So you want to partition the work so that, at least during the solution of the problem, there's no sharing going on. Okay, so this brings us to what is our standard tool for parallel decomposition, which is divide and conquer, right? It's also called recursive decomposition. And the idea is to solve the problem, first you say, well, is it so small that I could just solve it sequentially? And if so, just do that. And if it's not, divide it in half and recursively do the same thing. So we'll keep slicing the problem in half and slicing the slices in half and slicing those slices in half until the slices get so small that it makes sense to just solve them sequentially. And then when you can think of this as a tree, when we get to the leaves of the tree, we've done some sequential computation, and then we have to combine the results up the tree, right? So in our add up a bunch of numbers example, combining the results was simply take the result of this half, the result of that half, add them together. So this is the pattern that you'll see in all parallel algorithms. Decide whether you should just solve the problem by itself. If not, split it into some number of subproblems, solve the subproblems independently, maybe in parallel, maybe not. It's independent of whether you actually have the cores to do it. You could do this on a single core machine and it still works fine. And then when you've solved the subproblems, combine the results. So the nice thing about this is it's simple. It's fairly easy to read, and if your problem is already defined recursively, like you're doing a search on a tree, it's even more natural. We don't have any shared mutable state because we've partitioned the data set that we're operating on. And one of the other things that this structure of computation gives us is it allows us to start keeping those cores busy early. Right? We don't want to do a lot of work to divide the problem before we hand off tasks to any of the other cores, because while we're getting set up, all the cores are sitting around. Right? Every cycle you spend getting the problem decomposed is like 16 or 32 or 64 cycles you're not using because you've got a bunch of cores waiting for work. But the other cool thing about this is that the decomposition is dynamic. I didn't bake into that calculation how many chunks to slice the work into. I didn't bake into the computation how many tasks to have. I expressed the problem in a manner that's amenable to decomposition. If the threads are available, it'll use them. If they're not, it can work sequentially. If there's a lot of data, I can partition it. If there's not a lot of data, I'll do it sequentially. So you can think of it as a way to express a problem in a way that's portable across a lot of different execution architectures. Okay, so to kind of illustrate, how this actually works, imagine you've got a big array of numbers, obviously more than 8 numbers, but 8's what's fit in a slide. So we're going to divide that in half. And we have 2 chunks of 4, and let's say we decide to divide that in half again, so we have 4 chunks of 2, and then independently we start adding numbers up. So really what this computation breaks down to is do 1 plus 2, do 3 plus 4, do 5 plus 6, do 7 plus 8, and do that in parallel if you can. So 3 plus 4 is 7, and 5 plus 6 is 11, and 1 plus 2 is 3, and then maybe these guys get combined first. It doesn't really matter the order in which this happens because eventually they're going to add up to the right number. Okay, so this is what we're trying to get. We're trying to get out of the way. We're trying to say, here's the structure of our computation, and whoever is ready to do some computation, just go ahead and do it. We don't have to coordinate. First, you have to finish the bottom level, then you have to finish the second level. It can all happen as the data is available. Okay, So does this work? Well, yes, sometimes it works, sometimes it doesn't. When doesn't it work? Well, in order to understand that, we have to understand where our costs come from. So in a perfect world, we would spend all our time computing and no time decomposing, combining, dispatching tasks, etc. Every bit of time we spend doing those things takes away from our potential parallel speedup. So we have to ask ourselves, how easy is it to split the data source? If our data source is an array, really easy. If our data source is a linked list, not very easy. How efficient is it to coordinate the tasks? This is mostly beyond the control of most parallel algorithm writers. Usually this is something that comes from the underlying runtime. Does the runtime give you an efficient primitive for handing work off to another thread? How expensive is it to combine two results? In the case of adding up numbers, combining the two results with just an addition, that's really easy. If I'm combining two sets, merging two sets is kind of expensive, unless I have a data structure that's really amenable to that, like a bit vector or something like that. So I have to be mindful of not only what are the splitting costs, but what are the combination costs. And then also, am I going to actually be able to keep the core busy doing computation? And that's largely a function of locality. And each of these can steal away from the potential for a speedup. So you kind of start out with a perfect score, and then each of these chip away at your score. OK, so the substrate we use for coordination in the streams library is the ForkJoin library. We added ForkJoin in Java 7. And it provides task management for finer-grained tasks, right? So the Java util concurrent thread pools were designed for coarse-grained tasks. These are designed for fine-grained, CPU-intensive tasks, not reading from files, not making web service requests, but doing computation. And it's specifically optimized for divide and conquer style computation based on the concept of work stealing. It's super efficient for this kind of task. And the basic operations are fork a task off and wait for a task to complete, fork and join. So this is an efficient substrate for the little concurrent primitive that I illustrated in the earlier examples, and has relatively good task management overhead. OK, so streams library. Most of you are familiar with the streams library. Streams are about bulk aggregate operations on data sets. And we describe these as possibly parallel aggregate operations on data sets, which is to say that you could do them sequentially or you could do them in parallel. It's not just tied to collections. Your data set could come from an array, a generator function, could even come from I/O. And we've woven support into the JDK library. All the collections have good support for decomposition. So the nice thing is it encourages a style of coding that's both pleasant to write and easier to read. You build up queries from some primitives like filter, map, reduce, sort, etc. And it's all lazy. It does one pass on the data. If it's parallel, it does one parallel pass on the data. And all of the operations can be done in parallel. But it's not magic parallelism dust. You can't just say dot parallel and expect it to go miraculously faster. So as an example, here's the kind of code that we used to write for groveling over collections. It's ad hoc. There's generally a lot of intermediate results. And if you translate the same thing into streams, you get a much clearer, easier to read. Do this, then do this, then do this, then do that, and then put the result in a list. OK, so how do we know whether parallelism is going to give us a benefit or not without actually running and measuring it? Well, we could look at our problem, and we could look at the characteristics of our problem, and we can spot the sources where we might lose. Okay, and those sources involve splitting costs, combination costs, and locality. The task management cost is handled by ForkJoin. We don't have a lot of control over that, but we do have control over the other things. We also have to look at, do we have enough data to get a reasonable speed up out of it, right? And so a simple intuitive model for whether or not you're going to get whether you have a chance of getting a parallel speed up is to take the product of how much data do I have and how much work am I doing per data item. Okay, so if I have an array of 1,000,000 numbers, n is 1,000,000. If I'm doing something really simple like adding them up, Q in this model is really low. I multiply n and q, and magic number. If it's like 10,000 or more, you've got a chance of getting some parallelism. If it's less, you probably are not going to get any parallelism out of it. Okay, so good rule of thumb. If your operations are computationally expensive, you're doing, cryptographic analysis, you don't need as much data in order to get the benefit of parallelism. Okay, so let's look at all of those sources that steal our performance away and think about how we would use them to analyze a stream pipeline. Some sources split better than others. And when I talk about splitting, there's a couple of things that, that come into play. One is, how much computation do I have to do to split a source in half? How evenly do the pieces split? And how well can I predict what the split sizes are? Because if I know exactly what the split sizes are going to be, I can use that to optimize some calculations. So the best is arrays. Arrays split really evenly. It's really easy and cheap to split them. You compute the midpoint. You say, I'll take the left half, you take the right half, and you know exactly how big each half is. The opposite end of that spectrum is linked lists. They split terribly. The best you could do is first and rest. And well, then you can't split the left half any more than that, so you're done. And the right half, well, you can take first of the rest and rest of the rest, and you get a very ugly shaped computation tree. So if your source is a linked list, or it's something that's like a linked list, like an iterator, it's going to split terribly. Right? So if you compare these two different ways of summing up the integers from 1 to n, the second one is going to parallelize terribly, and the first one is going to parallelize really well. Okay? So if we're used to thinking sequentially, then when someone says, how do you generate the numbers 1 through n? Well, start with 0 and then add 1 to each one. This is just like the problem G in our first example. Right? And so if you frame the problem in a fundamentally sequential way, you're going to get a sequential answer. If you frame the problem in a way that's amenable to splitting, like the range generator is, you'll get much better splitting out of it. Okay, so that's pretty straightforward. That's something you can spot. I mean, people will come to me and say, why am I getting terrible parallel performance? And you just point right at the source. Say, that source doesn't split. You're done. Right? Okay, so let's say the source does split. What else is stealing our performance? Well, the elephant in the room is locality. I talked about this a little bit at the keynote yesterday when I talked about value types. We want to keep the CPUs busy doing useful work. Waiting for the cache subsystem to cough up data is not useful work, right? And on a lot of systems, the limiting factor is memory bandwidth. If I have 16 threads all waiting on cache misses, I'm not going to get a lot of throughput because the only part of the chip that's getting hot is the cache management subsystem. So the problems that parallelize best are the ones that are array-based, because arrays get really good locality, and those that don't have a lot of pointers in them. So as an example, I ran these two stream pipelines, take an array of ints and add them up, or take an array of boxed integers and add them up. And I ran it on an 8-core machine, and I got a pretty reasonable speed up on when I had enough data for the ints, and I got a pretty lousy speed up for the integers. And in fact, like on the when I didn't have enough data, I got a pretty big slowdown. And the reason for that is locality, right? This is the data that I was operating on. In the summing the ints case, I get nice locality when I've sliced the array up into pieces. Every thread has a piece of it already in its cache. And it can just walk down the array and add up the numbers and not waste any time waiting for more data to come out of the memory. On the other hand, if I have an array of boxed integers, every time you go to get the next one, you're going to take a cache miss, and you're going to wait. And that's why we didn't get a decent speed up out of the boxed integers. So locality is sort of the elephant in the room, and it's something you sort of have to train your eyes to look for. It's not as obvious as the source splitting one. Another one that we're not so used to looking for when we're used to thinking sequentially is encounter order. Encounter order is the order that's implied by the source. Sometimes that's meaningful, sometimes it's not. If I have a list, lists are ordered. So there's a first element, there's a second element, there's a third element, and it means something to be the first element of a list. If I have a set and I ask it for an iterator, it'll give me the elements in an order, but the order's not meaningful. The concept of the third element of this set doesn't mean anything. It's not a sensible concept. So lists have a defined encounter order. Hash set has no defined encounter order. Now, some of the operations that streams give you, like limit or skip or find first, are defined in terms of the encounter order. And when you do that, you're undermining the kind of parallelism you can exploit, because it's not simply enough to say, I'll work on the left half, you work on the right half, because before we get an answer, we have to wait till the left half completes to interpret the results of the right half. Now, sometimes you're in a situation where your source has an encounter order, but it's not actually meaningful to your problem. And this can be an area where we're losing parallel performance for no good reason. If you find yourself in that situation, there's an operation on streams called unordered, where you can say, yeah, pretend this stream doesn't have a meaningful order. Just do it, on whatever data you can pull out of the data structure first. I don't care. I want the first one you can find. So operations that are encounter order sensitive, like limit and skip, if the stream is unordered, they'll optimize for that. Okay. Another big potential cost is merging. In our summing example, the merge overhead was really light because it was just adding two numbers together. But if I'm doing an operation like grouping by, where I'm grouping to a map or I'm grouping to a set, merging is pretty expensive. If I say, here's two maps, merge them into one map, well, you have two choices. You can pull all the data out of both maps and put them in a third map. That's expensive. Or you could create a fake map that is a view over both of those maps, and then as you go up the tree, you're going to have this like n-level deep stack of fake maps, and your access time to getting to the elements is going to be really poor. So merging expensive data structures like maps and sets can be really expensive, and as a result, a parallel operation that has an expensive merge step like this might be more, might take longer than the sequential alternative. Sometimes the sequential alternative is faster. So, if I did add up, take the numbers from 0 to n and collect them into a set, even with a reasonably large, a data set, 10,000 numbers, I had about a 4x slowdown going parallel on that, because I was spending all my time merging sets and not, rather than just, computing the answer. And it, if we illustrate it, you can see what's going on. If we take the same input source and our task is turn them into sets, all right, so I can turn that into a set, turn that into a set. But then when I merge them, I have to create a new set. And as I go up the tree, now I have two bigger sets and I want to merge those. I have to create yet another bigger set. And the amount of work needed here is dominated by this merging operation. So if you look at a stream pipeline, you should be able to see all the things that I just showed you. You should be able to say, that source doesn't split well. That operation is tied to encounter order. This reduction is going to be having a lot of pointer indirection, so I'm going to get bad locality. That merge operation is expensive. And you should be able to look at a stream pipeline and kind of know offhand whether you have a chance of getting parallelism out of it or not. So once you know the factors that can undermine your speedup, you should be able to sort of run this in your head. You don't necessarily have to benchmark it out. You can usually tell when you're not going to get a speed up. Now, sometimes it may look like you're going to get a speed up and you don't. That's when you need to measure. But very often you can just pretty much eyeball the stream pipeline and say, how well does it split? How local is the computation? How expensive is the merge step? Am I using operations that are going to undermine parallelism? So, okay, let me sum up. Streams are really cool. Parallelism is really cool. But parallel streams are not magic performance dust. Parallelism is an optimization. Sometimes it gets you an answer faster, sometimes it doesn't. So before spending time thinking about performance, first ask yourself, do I actually have any performance requirements, or am I just doing this for fun? This will eliminate about 99% of most optimization activity. For the 1% that's left, ask yourself, do I have rigorous performance measurements? If you don't, stop. This will eliminate 99% of the 1% that's left. And then, if you're serious enough to have made the investment in solid performance requirements and solid performance measurements, then measure to see if you meet your requirements. And if you do, stop. If you've met the requirements, then any effort you spend trying to make it go faster is really just entertaining yourself. So, streams are cool, parallelism is cool, have fun with it, but don't go crazy. Thank you very much. So I think we have like 5 minutes for questions. OK, so I'll take questions. If you want to leave, go ahead and leave, but please do so quietly so other people can ask questions. I'm sort of blind here, so wave wildly if you want to ask a question. OK, somebody waving wildly over there in the red shirt. Yeah, so the question is, there was a lot of hand waving on that NQ model over there, and one of the hands that was waving is, how do you measure Q? Is it lines of code? Is it clock cycles? Is it byte codes? Doesn't really matter. It's an approximation. But if you want to count operations, additions, comparisons, things like that, primitive operations is a pretty good rule of thumb for that. Any more questions here? Yes, hand waving wildly over there.
I noticed your if small enough in the parallel, the pattern for exploiting parallelism. How much craft should you put into the is small enough? I mean, should you dig into the hardware? Do you write that into the code, or put it somewhere else in your configuration?
Yeah, so the question is, one of the other hand-waving items was when we do parallel decomposition, we say, is the problem small? If so, solve it sequentially. This is, in some sense, a function of what the problem is, right? And so if you're sorting, you're going to come up with a different threshold than if you're just adding numbers together. But the good news is, you don't have to be very precise about it. As long as you avoid the extremes of way too big and way too small, you're generally OK. So if I'm adding numbers together, if I use a threshold of 1, that's way too small. If I use a threshold of 10,000, that's way too big. But if I pick 50 or 100 or 500, I'm going to get about the same speed up. So a good rule of thumb is, ForkJoin framework is efficient enough that if your computational chunks are on the order of a few hundred clock cycles, then you're in good shape. So, that generally means splitting chunks down to as small as 50 or 100 elements is generally a good rule of thumb. You can, of course, tune this, right? If you're writing your own parallel algorithms, the streams libraries, try to do a little bit of tuning on their own. They also can look into the ForkJoin framework and say, how long is your work queue? Do you have threads just waiting for work, or are they all like backed way up? And that can be also an input into the split versus compute decision. But as long as you avoid splitting so fine that all you're doing is forking tasks and managing them, and splitting so coarsely you get no parallelism, it's pretty forgiving in the middle. Kirk, talk loudly. Yeah, so the question is, right now, you don't have a lot of control over how much resources you use. You do a parallel computation, and it gets executed in the common thread pool, which is set up with a fixed parallelism, and it uses all the threads. And so the question is, is there any possibility that there will be finer grained control over that? And the answer is yes. We are contemplating giving you some policy-based control over that. What we haven't figured out is what are the right knobs for that. And we know what the wrong knobs are. The wrong knobs are how many threads can I use, what pool can I use, et cetera. But the right knobs might be a measure of how big is Q? How big do I think Q is? Do my tasks do things like I/O, in which case I would want to split more aggressively? And do I have a target for what percentage of the thread pool might I want to, what percentage of the available resources might I be willing to consume? So we haven't quite formulated what the right set of policy knobs are, but it seems entirely reasonable to have a policy that you can put like as an argument to the parallel call and say, do the execution with this policy. But all the suggestions people have made so far about how to specify that have been worse than the disease, so we haven't done that yet. And I think that's
all the
questions.
time we have.
All right,
So
thank you very much.
Brian. Yeah.